Thank you, everybody. Thank you for the nice introduction and welcome. Thanks for joining. So, as the title says, we will have a small look, like an introduction to how speed up Python without hardware acceleration. What are, first, hardware accelerators? These are specialized devices where you can offload certain tasks other than your normal CPU in order to, so to say, speed up your workload. So here you can scan the code I'm going to present. We will have some little examples along the run, so you can reproduce yourself at home as you wish. So what are the main points we are going to cover today? First, the first question is Python slow? Maybe most of you should say yes, but we will try to understand how to rephrase the code in some manner to speed it up. Second, we will have a small introduction of a kind of toolbox of instruments to speed up these examples. And then I'll show some toy examples and also real-life examples, more complicated ones, from my high-energy physics experience. So, first, let's introduce the stage, talking about Python itself. Python, as we know, is a interpreted languages. Rather than a compiled one. And here, I guess most of you already know this, but I just wanted to refresh a little bit in order to understand what does Python under the hood when we run the code. So on the top row of this diagram, we have the compile language pipeline, where we have our source code, which is compiled with a piece of software called compiler, and which outputs machine code. Source code, of course, is human readable. Machine code is not. And this is highly optimized for the specific platform we are targeting with our compilation step. After that, of course, we can execute the binary code and output a result. On the other hand, an interpreted language runs a single step from source code directly to the result, and which includes also the execution step. The source code, again, is human readable and is written in your interpreted language as you wish. But the interesting part is that the interpreted is really a piece of software that should target the platform where you are running from. And this is a main object that you want to have, of course, to run your code. So I tried to summarize a little bit pros and cons of the two words. Compiled languages, we can say you can have private code in the sense that you can circulate your machine code after having compiled, so provide the end user only the compiled code. This is, of course, not open source, as you may understand, and yeah, it could be a pro, but not everywhere. Of course, compiled languages have faster executions because you have fully optimized through the compiler your code. And however, they lack of portability, as you have to target a specific platform in order to run it. Another pain could be given by a full code compilation, which means that of course, when you compile your code, you cannot compile part by part, but you have to compile everything. And this can be a problem. Well, maybe it can be just an overhead when you're testing your code. So if you want to test a single piece of code, you cannot compile just just that part, but you have to do for everything. On the other hand, the interpreted languages are much more portable, since you just have to install the interpreter for your specific machine, and you can run the source code as it is. They are easier to debug, since the interpreter goes line by line, interpreting your source code. Yes, but all the cons that are listed here is, of course, the other side of the coin with respect to the compiled ones. So one point, of course, is that they have slower performance in terms of the overall execution and interpretation, and that's why we are here today. Another thing that characterizes Python is that it's dynamically typed, and this is something that goes under the hood when you run some piece of code. Actually, the interpreter doesn't know exactly what a variable is. They just know, so the interpreter just knows that a variable is a Py object, which is natively a C struct, if you are running C Python, of course. As Python carries inside the objects many informations, since it's a high-level programming language, it's really flexible, but it has to implement some type checking that slows down your code. So this is probably the main issue when you have to deal with this slowness of the Python language. Here you have two kind of codes, C code and Python code, that do really simple arithmetics. Just load two integers inside variables and adds them in order to retrieve the results. But you can see on the left and on the right that the instructions translate into different operations so that the CPU has to undertake. So on the left, we have the C code that takes just four operations. On the right, we have to check mostly every time what a variable contains, what's the type of the variable, so type checking. And also, we have to understand which kind of operation the CPU has to do when adding two variables. On the top, you see that, in fact, the Python objects, even if you're talking about really simple ones, Python integers, contain many attributes. They have this list of attributes in their C Python implementation, and only the actual value is only stored in the last one, so the digit ob-digit attribute, which is it is basically a pointer to an integer in C. This, in turn, we can say that the C Python implementation has several layers of abstraction. So many of the variables and objects that you use every day are not what you think what they seem to be. For example, the numbers from 0 to 256 are implemented as singletons. So whenever you declare a variable that contains an integer in this range, and you declare another variable, both point to the same memory address. Sorry? What do you mean? Okay, it depends on the Python, I guess it's Python version, right? Yes, sure. Okay, thank you for the clarification. At the same time, the very first data structure that you can think of, so a vector, a list of numbers in Python, for example, is not implemented as a C array, as you can imagine. The object that mostly resembles a C array is a Numpy array, which is a wrapper around a C array, actually, which is a contiguous memory buffer of values. And on the other hand, Python lists are different. So they are implemented not as pointers to values, but pointers to memory addresses, pointers to pointers, sorry. So this way, the memory access of when working with Python lists and making operation on them is can be difficult, is not so optimized. So this was just to a little bit of introduction to set the stage, why we should think that there is something that it can be made more efficient. And now let's turn to some examples. We are talking about Python here, and just a simple example of a matrix multiplication. So we are multiplying two matrices. Here in these examples, they are both square matrices with sides 100 by 100. And as you can see, we are doing this element-wise with for loops in Python. This is extremely, let's say, inefficient due to the type checking and inefficient memory access by Python list implementation. And so this is also cubic in the as a complexity in the number of in the sides of the matrix. Okay, now let's have a look what a first operation that is more efficient can be. So NumPy. Using NumPy, we are, as I said before, we're using mostly wrapper to C arrays. And as you can see, there is a specific operation already implemented, which is the NumPy matmul operation that takes two matrices, as you can see in the red box. And this is way faster since it uses C under the hood. Yeah. Okay. So let's have a look at the other tool, which is Numba, which can in a way implement just-in-time compilation that can help you to speed up all the Python code that we have seen in the previous slide. So this is another way of tackling the problem. And as you can see, the only thing that we have to do is just decorate the matmul function that we have implemented before and run it as it is. The ngit decorator take from Numba library, does everything on its own, and allows you to have really efficient operations. Yes. The last idea that I wanted to show you is using TensorFlow to speed up your code. So the idea is that we want to use TensorFlow primitives. So we have to think vectorized, like in the NumPy example. But using only TensorFlow primitives, you are able to speed up all the operations and allowing TensorFlow to run in its graph implementation, which means that by this mode, under the hood, TensorFlow is implementing a graph of operations, and whenever you feed the inputs to this graph, it instantly provides you the result because it has optimized along the way all the graph structure. And again, an interesting part here is that since you have implemented everything in TensorFlow, porting to GPU, the code is completely free. The only problem probably is that you have to think vectorized. And this is not always as clean as it would have been like in the for loop example in the first Pythonic element-wise operations. Okay, so let's turn to some toy examples. Here we have Pairwise Distance. So we take a set of endpoints in k dimensions. The goal is to compute the Euclidean distance between each pair of points. As we can imagine, this is a complexity of order n cube. Oh, sorry, maybe this. Oh no, okay, yes, because we have also k dimension, which can be large. Sorry. Yes, n square k could be better. Yes, sorry for the typo. Okay, yes, we made multiple benchmarks of this problem. The different implementations are available in the GitLab repository. And as you can see, the Python loop is the slowest one, as you can imagine, of course. And the other bars are about an order of magnitude, or sometimes 2 orders of magnitude better, like in the case of Numba and TensorFlow itself. The one which was really surprising to me was the SciPy one, which provides an interesting function in the library called cdist, and it was really fast. However, all of this code runs just on CPU. We will see in the following examples that GPU actually has incredible improvements. Okay, the same, another example is a Monte Carlo integration, which is in the physics domain a really relevant problem. Monte Carlo means that you draw random points in an integration domain and you evaluate the integrand function, and after that you apply the equation that you see at the bottom, which is mainly a mean over the function evaluation. So you take n function evaluation, you multiply by the volume of the integration space, and then you get the integral. The thing that it's really relevant to the use case is that the Monte Carlo integration is parallel. So you can either draw one point at a time and evaluate the function, or draw an array of points and evaluate a vectorized function. And doing so, we see that the different implementation of this Monte Carlo integration has achieved mostly the same speed up factor that we have seen before, around 2 orders of magnitude for Numpy, Numba and Tensorflow implementations. Now, just to let you know that this is not just useful for simple use cases and toy examples. I just wanted to introduce you to a more complex example that we have experimented at during so in my physics research, which is interpolation. These are PDFs, which are mostly the way the protons are described in physics theories. And as you can see, the problem here is just to provide an interpolation of between points in a grid that is pre-computed by some physics experiment. So the idea is that the user wants to draw a number inside this grid, 2-dimensional space, and you have to somehow return the interpolated values. Of course, there are state-of-the-art tools, which is called this lhapdf, which is written in C++. So we are going to compare C++ code against Python code with the vectorization provided by TensorFlow. And as you can see here, on the left side, we have lhapdf, which is sequential. So it requires 2 for loops. You have to draw a point in x on the x-axis. You have to draw a point on the q-axis and then call the function. The actual computation, instead of the our vectorized tool using TensorFlow, uses instead all the vectors as inputs. And as you can see on the plot on the right, we have really big enhancements of in terms of performance. In the green curve is the lhapdf C++ code that can run on CPU only. The blue and the orange curve instead are our code, which is able to run either on CPU or GPU as well. Since it's written in TensorFlow, it's ported seamlessly to whatever device you have. So the interesting part is that you receive enormous speed up if you're using a GPU. So the orange curve here. On the bottom row, you see the ratio between the performance of each line of our tool against the green line. So 100 are almost 100 of speed up. If you consider that we have order of 1 million of points in the vector as inputs. Yes, so this is just to show it's not important the meaning of this kind of more complex tool, which is called MadFlow. Is a complex Monte Carlo integrator, which includes also PDF flow in his toolbox. The message I wanted to convey is that we are again comparing our code that can run both again on CPU and GPU against another tool, which is the state-of-the-art, that is C++. Also, it contains some Fortran, so it's a really complicated piece of software, and it's called MG5. And you can see MG5 in the bottom row of bars. Our tool is in the first and the second. The first is running on GPU. Second runs on CPU. And as you can see, this is done for different problems, which are these ones are physics problems and are ordered by complexity. So the easier one is the one with 3 diagrams, and the last one is 267 diagrams, which means that it's way more complex and requires more time. So as you can see, we experience a good speed up. The speed up, the efficiency speed up decreases as the number of diagrams involved increases, but this is because the tool is really complex one, and maybe sometimes TensorFlow provides some overhead in their operation. Just last slide about last example. This is another use case, is quantum computing. I know that this group of research provided a library called KiboJIT. JIT stands for just-in-time compilation, which is another way of thinking of the pipeline of an interpreted language, which means that instead of interpreting the whole source code, you first just-in-time compile a piece of codes in order to speed them up. And yeah, this is a quite complex plot. Nonetheless, I just wanted to show you that on the right here, the blue curves are the one that implement GPU running, so hardware accelerated, and they implement, so they show important factors of speed up with compared to usual CPU running, and also using Numpy backend, for example. So concluding everything up, yes, I just wanted to say that Python code is very flexible and improves readability, so it's good to implement our tools in Python. And nonetheless, we have to take some care in defining our operation, since the first thought of a person can be, I just implement this as a for loop, which is of course more readable and more easier to think about it, but then the performance are not so good. So there are many libraries out there. Numpy, TensorFlow, and Numba are just an example. There are many others. Yes, it just experimenting a lot and trying to extract the best out of our use cases is the best in these cases. So thank you very much. Let me know if you have questions. I'm here to answer.
Thank you so much, Marco. We have two questions. Do you think TPUs would further improve performances when using TensorFlow?
Yes. So TPUs are for Google's only, if I'm correct. First, the problem is that they are not as spread as the GPUs. I tried also with some, let's say, version, not the latest version of TensorFlow to use them, and those were not all the operations were compatible with TPUs. So it's quite difficult. Maybe nowadays with the latest version things have improved, but I cannot tell you out of now.
Okay, thank you. And the second question is, what is the point when you should start considering hardware acceleration? Is there a general rule to consider?
Well, as I said in the last slide, you have to experiment. Of course, every use case is different, but the main rule of thumb could be that you have a lot of points that undergo the same operations, and all of the operations are, let's say, independent. So instead of taking one point at a time and repeat the operation, you change the paradigm and you think about like SIMD, so SIMD extractions, which means you undertake all parallel execution for all your points.
Thank you so much.
Thank
It
you.
was a great
Thank
presentation.
You, everybody.